Oh, what's up? What's up? What's up? Welcome back. Today we're working on kind of my Git GUI. So background info here is that I've been working on this Git GUI because I don't really like many of the ones that I've tried. I feel like I can make something that's like better tuned to like my own usage. So this is what we have right now. Is like we have this thing where I can click on the log, I can see commits, and I can see the diffs of the things in the commits. Simple. Easy peasy. And what we're working on today is we're working on the diff algorithm. So how does the application know that like, oh, here's what was in the file before and here's what was added in this commit? How does it calculate this? And it's using, as far as I understand, what everybody uses, which is some version of the Myers diff algorithm. So there's this blog post by James Coughlin who basically kind of walks you through exactly what it's doing step by step. But essentially, it's like a glorified breadth first search algorithm. So the idea is you set up your two sets of things, right? So in our case, in our application, it's like lines in files, right? We say, okay, so we have a current file, and we could say the content is ABC, ABBA. Maybe we should write this down. ABC, ABBA. Right, so that's our starting state. And our ending state is the second thing, CBA, BAC. So, CBA, BAC. And the idea is that we can get from ABC, ABBA to the other thing by saying, well, first we're going to like delete A and B because those don't line up. Then there's like a C here and a C here, and then we can like add this B in. Now there's like an A and a B in both of them, so we can just keep going. Here there is, we like delete the B and then there's like an A and then we add back the C, right? You can kind of like slowly step by step get through this like transformation. And they represent this thing as like a graph. So they say the x-axis is your starting string and the y-axis is your ending string. And the idea is that like every time you like move towards your starting string, you're consuming a thing from the beginning, from the start, and every time you move along the y-axis, you're consuming a thing from the end. So the idea is if you move right, but you don't move down, that's like a deletion, right? You're like, this thing is not in the second string, so I'm going to delete it, and then if you move diagonally, because they like, you know, there's a C here and a C here, that is like no change. And then if you move down, that's like an addition. So this sequence here is like basically what I just did, right? You delete A, you delete B, you keep C, you add B, you keep A, you keep B, you delete B, and then you add whatever, right? Like that's how they're doing it. And so Myers presents this like algorithm. It's essentially like, hey, you can like represent this BFS in like an intelligent way. So you basically have to like keep less data. And so this is like the algorithm here. They say basically they create these like tracking variables D and K. So they kind of say D is like each step you're taking in the algorithm, and K is kind of like where you are, like how many deletions versus insertions you've made. So essentially like how far are you like to the top right or bottom left of this graph. And then you just do a breadth first search by like, you kind of say like, okay, well, I'm going to make a tree of these things, and as if I see a diagonal move, I take it no matter what. It's free, I'm going to take it. And you see like, okay, how do I get to the end fastest? Well, it's like you're going to like branch out and you're going to hit these cases where you see long diagonals. You're going to like shoot down to the end of them, and you're going to get to the end faster when on the path that has more diagonals. Keep more of the same thing, less edits. Great. The problem with this is that in order to figure out the path you took to get to the right answer, you have to remember all possible paths as you're going. So this is like an O of n squared algorithm, right? Because you have like, you have to keep, here, let's see. It's like sum of increasing number, increasing diagonal. It's like, I can't remember exactly. It's like on the order of n squared. So I see cases in like my current implementation where I'm like, it tries to take up like 360 gigs of RAM to compute like a 1,000 line diff. And it's like, that doesn't make any fucking sense. So, all of that to say, there's a linear version of the algorithm that I want to try and implement. But it's hard to implement, especially on stream. If I want to do it on stream, then it's something like just implementing the algorithm is not going to make a lot of sense. And also, I'm not like 100% sure that I get the algorithm right now. So the idea is we're going to make a visualizer for this, try to step through the algorithm, and then once we get through like that, then we can like just add in the linear portion, and then hopefully we'll have a better understanding. We can see something visual, and it'll be good fun. So we got to at the end of last stream was we have this grid that kind of represents what was here, and it shows like our current state. It's like, well, kind of. We got to the point where we were drawing we hit the next button and it runs a step of the algorithm, and then it shows this green dot, which is supposed to represent where on the graph we're looking at right now. But it's crashing and not working, so we're going to continue on with that first, and then hopefully we can try to visualize like movements of some form and maybe show like many moves at once. Not really sure. And then maybe show like the backwards pass as well. Okay, so I think the first thing we have to look at is why the fuck is it crashing? And that is in main.rs line 134. So that is here. So he's saying, hey, the algorithm has not finished yet. I'm trying to extract some debug info. And in there, he's saying, I'm trying to get my current X position. So the way this works, Imogen3, thanks for the prime. Appreciate it. Why is my indexer not working? I would like to jump to definition, please. Oh, there, it was just taking a while. Okay, so the idea is that they have these variables D and K, where D is kind of representing, maybe we'll screenshot this and bring him into Paint. And the idea is, what the fuck? I said, what the fuck is going on? Screenshot, copy, says it's in my clipboard, paste, hello, that's so fucking annoying. Save, or maybe there's a open with, export to Paint, here we go, okay. So it's approximately like D is this way and K is this way. And so you can kind of extract your X and Y positions on this graph, where this is X and this is Y. You can kind of like extract these by D and K. So here, there's this like complicated set of ifs where he says like, hey, if I have D and K and I can like look at the stored X position in my graph, and figure that out based off of if like I think that I came from the left or right side. If like which branch I took to get here, he can kind of like derive X from that, and that's failing in some way. So probably because we're calling him with an invalid D and K. So it'd be interesting to see what our D and K are. And I guess it's not like this. It's self D and self.k, which I think you can't do in these braces, so I think I have to do those externally like this. Okay. Oh, I forgot to write down the time that we actually started working on this. This is probably around like sometime before 8:30. I don't really know when. Okay. So D goes D0K2, D1K1, and then he crashes at D1K3. Aha! Okay, so the way this works. If we were to draw D on this axis and K on this axis, you kind of start with like one node here. So this is K, 0, -1, 1, -2, 2, etc. He can go like left or right to like D1, K, -1, or +1. And then from here, he can go to D2, K, -2, 0. The 0 connects to -1 and 1. And then this can be like, or 2. So the idea is that at each level of D, you can only increment K in steps of 2. And I think what happens is somewhere we adjust K, but we don't handle like the edge case of it of where it has to wrap. So I guess we should just, I think we should just do this down here. I don't see any reason why it has to be up at the top. I think. Okay, that looks better. It's not crashing anymore. And eventually the algorithm finishes because it stops drawing the circles at depth of 8. And I think that it was only rendering on the diagonals, which makes me think that there's a bug in our rendering of the color, which there definitely is. This should be X here. We should check if the Y index is with the debug info Y and the X index is the debug info X, we should draw that thing. So now, if we look at this, we should see it kind of ping-ponging along the diagonals, which it is. And interestingly, there are cases where it's kind of going outside the possible domain of edits, which makes me think that there's actually kind of like an optimization we could do here in terms of the structure. Because here it's doing D4, so 0, 1, 2, hold on, let's look at this again. 0, 1, 2, 3, 4. So I think it's actually like rendering like way out fucking like here. Which is just not a valid position. So that looks like maybe like a potential optimization in the algorithm. Because like it's like stupid to look at this. But that's fine. That's fine. For now. We will flag that as like a thing to maybe look into in the future. And okay. So we've now kind of like successfully showing the current node on the graph. That's great. And now what we want to show is like, maybe we want to show how it got there, which move it took from the, like, because on each node it decides, okay, which option of like how to get here is like a better option for me. Actually, let's show something, a version that has like stuff in common. So we can look at, where do we like set our numbers here? So we're diffing like 5, 6, 7, 8 to 1, 2, 3, 4, or 1, 2, 4, 3. Let's diff 1. Maybe we'll do like 4, 3, 1, 2. So the idea is that maybe like these two areas should swap. And I think what we should see is we should kind of see like the green chunk, the green thing. He should be like jumping around if he sees like a potential diagonal. So here he's like at the beginning. Now he looks down here. Nothing, nothing, nothing. Now there's just a bunch of, we're not seeing anything on the graph. Interesting. Interesting for sure. So in this scenario, we just saw a lot of positions not shown, which seems kind of fucked up. Maybe we should like log our X and Y positions. So maybe we'll say print line dk and x, y. And this is going to be our X and Y. I don't know if there's like a bug here or if it's kind of wrong. Okay. So here we have x0, y1. Great. x1, y0, blah, blah, blah. Nothing here is crazy yet. So now we end up with x2, y5. And then x3, y4, x4, y3, x5, y2. Oh, hold on. Then we're getting y6? When like there's only 4 values on this whole thing. And then we end up at x4, y4, which is... Oh. I think we fucked up a little bit. So this graph shows... the starting point as of being completely empty, and then the first thing being like a deletion. And we've kind of stored like the first node on our visualization as a letter. So I think we just have to fix up our visualization here to maybe we should show that same thing, I guess, where like the first element is not a letter on the graph. Okay. Okay. So here we have the drawing code for A and B, which are two strings. So here where we have like the lengths of them -1, that's now the length because we're adding an element. Here we're special casing the first thing, but I think we don't have to do that anymore. Yep. Here we have to fix our position spacing. Oh no, this is fine. Okay, yeah, this is fine. So this is wait, is it? I think we adjust each element to be one to the right or something. That sounds kind of correct. A laid out dot iter enumerate. Okay. We can see if that looks right. So on the x-axis, we should see... Nice. Okay, so here we see the letters laid out over here, which is great, or the numbers, I should say. But the grid is still the wrong size, but we can fix that. We'll get there. So we do the same thing for the y-axis. This guy goes here, and this is idx plus 1. Okay, and now we have to handle... I guess these grids have to be equal to the length of the elements, not less than. Let's try that. Not quite right. We're not handling where are we drawing like the circles? The circles are down here. So these guys also have to be equal to and these guys have -1s that they shouldn't be using anymore. There we go. Okay, let's try to visualize this again. So we see him go here. Oh, there we go. Okay, he jumped down to the bottom. That felt good for a little bit. So here we see he's gonna jump down to here. Then he's gonna continue on, and then here he's gonna notice that he can jump down this diagonal. So he's gonna see at this point we're not drawing the diagonals yet, which we should. But he's gonna see like there's a 1 here and a 1 here and a 2 here and a 2 here. So he's gonna jump here and then go blump all the way down here. I think. No. That's what I thought would happen. Oh, but he does it here. X2, Y5. 0, 1, 2, Y 0, 1, 2, 3, 4, 5. Clearly, we need to show travel. Because this is hard to track the way it is. So 1, we have to draw the diagonals. 2, we have to show the path it took along those diagonals. So maybe the first thing that we do here is show diagonals at all. Show diagonals on graph. Okay. So what does that look like? I guess in our graph rendering code, for each circle we draw, we can also check the previous or like the next position, I guess. So we can say if y idx plus 1 in self B hold on. I guess if y idx in self B. Yeah. is equal to self b get x idx a get x idx. Yeah, so if they're the same, then we draw the diagonal. So we'll say painter dot line segment. So here I guess we will say line end, or x end is the x idx plus 1, and the y end is y idx plus 1, I guess. And then we'll draw a line segment. So here I think we can just go whomp. So this is x pause x end, so y end, x pause y pause to x end y end. We draw a line. And I think that we should see diagonals on the graph now. Oh, super straightforward. Nice. Nice. So that makes sense. So here we go. We're at 4, 3, and then we have to move diagonally to 1, 1, 2, 2. So those diagonals exist. And then I guess at the end here, where there's like an end state off the edge of the graph that it's showing, which it shouldn't. So I guess we should say if y idx is less than self.b.len and x idx is less than self.a.len. I think that makes sense. I think. Yeah, okay. Looks good. Okay. Okay. So now we want to I guess we want to show the movement is what we want to see here. So let's look at 22, 20. We want to show last move on graph. So we need to see where it came from, which is like a thing that we already kind of do in the algorithm. When we like generate the diff, we do this like backtracking stuff. So I guess here we could return prev x and prev y. So where did we come from? And in here we're just gonna do whatever the fuck we did here, which is kind of this whole section. So what does that look like? We have like pub function, what is this doing? This is saying given a d and k, what was my previous k, and then from there, what were my previous x and y? So I guess this is kind of like a helper function of some form, I guess. It's like function prev dk prev k, I guess we call it. So we're kind of saying like, where did we come from? So given a trace and a current k value, I think this has to be mutable, which is a I64. What was my last k? Which is this. And I guess we need a d value as well. And so maybe this should be prev dk, and this will return 2 I64s. Prev k is fine, because the previous d is always just d minus 1. So that's this guy. I guess we can call it get prev k so that it's we don't have name collision. And so here we would pass in the trace d and k. And this goes away now. Cargo test to make sure that we're doing the right thing, but that won't work because the debug info stuff that we were adding is no longer functional. So we can say prev k is equal to get prev k. With all of these parameters. And then we can also pull out this like get prev x. Get x for dk. Yeah. Which I guess just doesn't need to be a function here. That's basically already exists. So here we can say let x is equal to self, or prev x is equal to self.trace, self.d, self.k. Yeah. Which I guess is get mute, and then we dereference this. And then our prev y is the prev x minus prev k, because of like however this is set up. Okay. Oops, this is prev y. So now for our tests, because we factored that thing out, hopefully we didn't break anything by factoring that out, which is great. And then we can go into our eGUI code. And when we look at our debug info now, we should pick the color of our line based off of... I guess we kind of draw a new line given this debug info. So we kind of just do a stroke that goes from debug info.x. Maybe we'll call this like function draw step or something. Whatever, it doesn't really matter. This will have to get cleaned up eventually, but for now I'm just gonna do it in line because that's where my head's at. So this is gonna be like let line start is equal to grid y idx to pause, and this is going to be debug info.prev x as usize prev y, line start y, and then we do the same thing for x, and then we do ends, and this is y and x. Okay. These guys need x here, and here we just say line start x, line start y, to line end x and line end y. Chillin'. Oops. Let's check the visualization now and see if it did anything. We might crash for some reason, but it looks like we're chilling. We need to set the color of this stroke to let move stroke is equal to stroke, and the move stroke color is equal to color 32 green. So this should show us how we get from one state to the next. It's certainly not doing that. Whatever we're doing, it's fucking wrong. So this is line end x twice. This is not using the move stroke. It's just multiple bugs in that like one line of code. Okay, wait, that's almost okay, except for the case where x and y are off the grid. No, that doesn't look right at all. Okay, I guess we should say if debug info prev x is greater than 0, and debug info dot prev y is greater than 0, and debug info dot x is greater than 0, and debug info dot y is greater than 0. This is the condition where this is allowed. Otherwise, we can't show it on the graph. Now we're just not showing any lines at all, which is not good. So it would be interesting to show, maybe. Can we just print the debug info? That will probably help. Is this printable? We will make it printable, and that makes our lives simple. And then here, yeah, we'll just say let red is equal to this guy, and then we'll print line the debug info, and then we'll return him. Okay. So x 0, y 1, and then we're seeing prev x 0, 0. So I don't understand why this line isn't drawing. Right? Because certainly we should be drawing green here in this case. Which means that we must be making a mistake. Okay. Prev y 0, 0 to 0, 1. I wonder if, like, drawing the lines on top of each other is causing problems. Like, I wonder if there's, like, Z fighting. No, here he should, like, 100% be drawing this line. Maybe we should print out basically all this stuff. So delete word, find equals, delete, next line. And for each of these, we're going to say yank, paste, then put in squiggle brackets. And then we can end this. There we go. Like, surely I just don't understand something. Why is it... I forgot equal signs everywhere here. God damn it. Okay, let's try that. Let's try that. Okay, yep. So how did we get here? Why is this one not working? Because the previous y is -1? That shouldn't be possible, right? Am I high? Previous y for this guy should be coming from one of these two. Interesting. So it looks like we're making mistakes. Somewhere it doesn't make sense. Which must be when we extract the debug info. This, like, prev x and y must not be working the way we expect. Because I'm an idiot. Prev x comes from... This is just stupid. What am I doing? D minus 1 and prev k. I'm just using the wrong fucking variables. So I was just, like, looking at, like, garbage memory and just hoping for the fucking best, I guess. And he doesn't like this because we're asserting somewhere k is greater than or equal to -d and k is less than or equal to d. So we're hitting some sort of edge case here in 294. Yeah, so that's what we just added, obviously. Right. Because we kind of increment this stuff before we should. We're, like, looking at... Oh, no, this is fine. So we get our current x position. Okay, hold on. How the fuck does this shit work? How does this work? Get previous k. Yeah, so we look at d minus 1, k minus 1, and d minus 1, k plus 1. Yup. I guess there's a chance here that d is 0. So we kind of maybe have to special case that. So we have to do like if self.d is equal to 0, greater than 0. We do this. I think, maybe. Else we maybe just hardcode them as 0 or something. I think there's like a I think we're doing something stupid in how we're representing this graph, but like I think I'm doing something stupid, but it's fine for now. We can always clean it up later. This is why visualizing is good. Okay. Yes. No. Well, maybe. It's drawing something off screen, which is maybe part of like the way the algorithm works. Yeah, okay. So I think there are cases where X and Y are getting mapped to like in unreachable positions, and just kind of like by nature of the algorithm, they kind of like correct themselves later. Let's go back to drawing all of the lines. And I think this is looking really promising. So here we're seeing that we try a addition, we try a deletion. Here we move from that previous addition, we go down again. And from here we say, well, we had to pick if this position is going to come from an addition or deletion. We decide it comes from the deletion because I think we favor deletions, if I remember correctly. And then he goes here and he says, okay, yep, and this is where it starts getting interesting, is now he was here and he is immediately shot down to here. We kind of didn't really like visualize that jump, I don't think, which kind of would have been nice. Why don't we do that? It's because it's greedy. He starts here and then he sees the like jump here and executes it at the start of the next iteration instead of the end of this iteration, which is kind of unfortunate. Kind of unfortunate, because it would be nice to be able to see that. That's like the interesting part. That is the interesting part. So it's almost like our like graph representation, our like visualization representation. Should almost try to show that. I'm trying to think if there's a way to show if we're like off by 1 on what we're showing. Maybe let me look at this again. So here we're saying we're looking at this node. We came from this one. Okay, yeah, I think we can just show both parts. So there's kind of like 2 parts of each move. One is doing the like addition or deletion, and then the second part is like following the diagonal if we see it. Right, so here we're kind of only showing the first half, but we should also show this if it's available to us. Because then on the next iteration we're going to move downwards, which doesn't exist, but that's beside the point. Okay. So I think that means that in our debug info, I guess our debug info needs to see the contents of A and B where U is a thing that implements partial EQ. And we kind of want to look at we want to do what they do in this step function, which is they say, wait a second. So while A is blah, 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 they do inject an X at that position in the trace at this position. So I think it's actually here. Our X position is just we're calling the wrong thing here. This should just be self trace get mute. Okay, let's see what that does. Because this should like encode that advancement along the diagonal. I'm not 100% on this. I don't really know what that's going to look like, but I think that's more correct. Nope, something about that's not working, right? Because we advance K immediately at the end of this. What if we advance K at the start? The idea being that after each step of the algorithm, we can look at the current D and K instead of the next D and K that's unresolved. That would mean that when we initialize, K would have to equal -2. And then I think everything else kind of just works for free. I think. We'll find out. No, he doesn't like that. Cargo test? Does cargo test like that? Okay, so the tests are still all passing, so it looks like we're crashing in like this visualization code. And probably because here we're probably using invalid D&K. So here we have to say if K is within like the valid range. So if it's not in the valid range, we're just going to return something that's like 0, 0, 0, 0 something. I don't know. We'll have to look a little closer at this later, but I think that's a fine fine workaround for now. No, he's still crashing. Where's he crashing? At 300. So here we're saying self.d is something, k is something. Why are we crashing? We're pulling out some invalid memory. I just don't know what it is. K equals -2. Yeah, so we're just... Oh, this is supposed to be OR. Classic Boolean algebra mistake. Classic. Classic, classic, classic. There we go. Okay. Nice. Okay, okay, that's pretty close. So here we started here, and then we jumped down, and then across. And then here we step right and then across. So we just have to like segment this line now. That's very close, very close, very close. So this debug info, he's got to show like a possible two-step thing. So this is like his current position. Maybe we'll just show it as steps. There's going to be a vector of x and y. And here, we're going to put in steps is, we took no steps yet in the initial case. Here, we're going to say that we we have to think about how we backtrack here. I suspect we should be able to draw the kink if we x inter is equal to self.x. So I think this will calculate the movement. This will calculate. This will say the movement plus the diagonal. So if we have like a, we start here and then we go across to here and then we go like down to here. I think this will be like the intermediate kink. I think. X inter minus okay. We'll see. We'll see. If I understand like this like representation correct. Okay. So here I guess we'll say let steps is equal to some vector of points. The first thing is going to be prev x, prev y. The next thing is going to be x inter, y inter. And the new thing is going to be xy. And then we just return steps. And then in this case, I guess we will also just return steps is equal to vec new. I'm not really sure about that, but I think that in this case, there's no movement to show. I guess we still want to show like our end position. So we'll say that steps is just vec of x, y. There we go. There's no movement, but we are still at some position. Okay. All right, check. Now the usage of this guy is going to be totally fucked in our main. So here, we're going to say the debug info is this. And I guess we're going to look at the last step to find the debug info xy, like where we're at in the, where we're at is like the last step. So we're going to say let last step is equal to debug info dot last, or steps last. And he's going to say, hey, that's not public. And I'll say, fuck you. Let's just make it public. Yep. And then I guess we'll say let color is equal to match debug info. How do I want to handle this? Now that this thing might not be there. If let sum last step is equal to last step. We do this. This is a nasty fucking if block. Jesus. This should be last step 1. This should be last step 0. Yeah, this is disgusting. Absolutely disgusting. But we'll clean it up later. And by we, I mean me off stream, you know? And then for here, instead of looking at this, we're going to say for step in steps. And I guess we don't want steps in steps. We want like windows of length 2. And if I remember correctly, windows returns the iterator over all contiguous windows and length size. Windows overlap. Perfect. That's exactly what we want. So we draw a line for each step, but we just have to handle the start and end differently. So the start is going to be step 0, 0 for the previous x. Step 0, 1. Step 1, 0. And step 1, 1. And we have to do the same like thing where we limit this to if these are valid U sizes. So we have to kind of say if any of these guys are less than 0, continue. Step 0.0 less than 0, or step 0.1 is less than 0, or step 1, 0 is less than 0, or step 1, 1 is less than 0. Okay. Think we're chilling? We'll see. We will see. Okay. Nice, nice. Hell yeah, baby. Look at that. That's sick. So now we see that we started here and we go plump plump. We try this guy, we try this. Come from here, plump plump. This is wrong. So we kind of need to clamp. I guess it's not the end of the world if we see that. Okay. Okay. Not bad, not bad. So I think that we can say we are showing the last move. And now we want to show kind of all of the last moves at once, maybe. This will be very useful when we start implementing like the linear thing, because the way the linear thing works is it kind of like walks backwards or walks from both ends until like they collide into each other. And so it'd be nice to like visualize the collision. So it would be kind of nice to like keep all of the last step shown at once. Okay, so let's think about that. Let's think about that. How do we visualize that? How do we visualize that? So I guess it's kind of like we're looking at each combo of, we want to look at each K value for the depth that we're at. I think. Let's just think about, okay, so how do we represent that? So I guess our algorithm he's going to want to export a chunk of steps for like each value of D and K. Each relevant value of D and K. Maybe all values of D up until the current D. Yeah, I guess we could kind of say like for each current head of the tree, right? We kind of have like, do we have this drawn somewhere? We kind of know that we are like here. Or say we're actually like at this point. So we're walking top to bottom, left to right. If we're here, we can show at the very least the last move for each value here. And I think that's what we want. We want to show like this, this, and this. So I guess we could just look at the current depth value and iterate from all K values that we like currently have and log where they came from. And I think we can generate that on the fly. Pretty sure we can generate that on the fly. So which means that we kind of just have to do this chunk of code in a loop. So let's say that this is a vector of steps. So the outer one will be steps. It's going to be for k value line segment. Yeah, that makes sense so far. And so here we can say first for k in negative d to negative d to d, yeah. Step by 2, because that's how this works. But only for valid values of k. So if k is greater than self.k, break. Okay. Then we just do what we were doing before. But instead of returning here, we're going to say let steps, okay, steps for k is equal to this. We have to be careful here because now we don't want to use self.k anywhere in any of this, I don't think. I think we just want to use like the current k that we're looking at. Self.k. So I think we just delete self on all of this. And then we can kind of return this thing, and then we can say ret push steps for k, or steps push, I guess. And then at the end, we say diff algo debug info steps. Maybe. Maybe. Maybe not, but maybe. And then in main, we should be able to then say for k steps in debug info steps. Yep, we're just adding another dimension here. We should be able to now say for step in k steps windows. This guy has to be like last map v last, because we want to see the last thing on the last thing instead of just the last thing on the thing, you know. This should be and then, I guess. Nice. And then I think everything else might just work. Definitely not working correctly. Okay, so something's something wrong there. Let's start by making sure we'll kind of bisect the problem. So I suspect that the bug is in this like debug info generation. So what we can do is we can just regress, or we can just like go back to what we were doing before. So we can just say for k in self. Oh, this is what it should be dot equals. I'm pretty sure that's it. Like I was going to debug, but then I just spotted what I think the actual bug is. We'll see. Somewhat correct. The dot is now rendering in the right spot, but obviously the lines are, well, maybe not there. Well, let's look again. Are the lines obviously wrong? MStar, thanks for the raid. Appreciate it. So clearly, whatever the fuck is happening here is not correct, right? We've never even fucking looked at this node. So the fact that somebody's trying to draw there is a fucking incorrect behavior. So let's bisect the problem again. So let's say Here we're just going to say for k in, the simplest thing to do is comment this out and say for k in self.k. So that way we should basically be doing what we were doing before and only show one path at a time. And this is working fine. So, like I suspected, the bug is in this generation here. So what the fuck is he doing wrong? This. This is clear. He's looking at the intermediate x value is for the current cell, like the current k, no matter what. So here we can just pass in k as a 964, and then this guy is using k instead of self k. And I suspect that over time we're going to learn that these functions will be just split out into like free functions, but for now we will leave them as is. So this guy's using k. Let's give him a little look skis. Okay, boom, 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 boom. Oh yeah, baby. Okay, that's not bad at all. And then so we move on to the next iteration. Boom, boom, boom. Okay, so now probably what we want to do is maybe like we want to like checkpoint the starts and ends a little better. Right, so like here we want to see this filled in as something. And probably we want to see this filled in as something too, right? When we get here, we kind of want to see like, hey, we have this and we have this. Maybe not. That's pretty slick though. So here we're already starting to gain like a little bit of an intuition about what's happening, right? We can see that like as we step the algorithm, he's starting in the top left and he's like kind of just walking diagonally, and you can see he's like, oh, diagonal, go down that path, please. Yeah, not bad. And we can also see some like room for optimization where we're like going off the edge of the fucking graph, which is like clearly not useful. Clearly not useful. Okay. I think what I want to show next is end state. Like continue drawing finished state. Right? Because like what happens right now is I slam this button and we get to the end and then we don't see anything. It'd be nice to at the very least see where that last step came from. So probably what makes sense here is the finished state here should just hold the last debug info. Diff algo debug info. And that way, because we're not really allowed to interact with the algorithm in that case. Oh, maybe we are. We should be able to. Let's unguard this if not finished thing. And let's just kind of see if this still causes crashes. We should be able to extract debug info at the end of the algorithm. And if we can't, then we're doing something stupid. Did I fuck something up? What the fuck's going on? Oh, because self.finished? No. Hello? What the fuck is going on? Unknown field? What did I just change? Wasn't this just fucking compiling and running until I removed this? I guess I lost this and then somehow, probably by like undoing too much and then like modifying. Yeah, I'm pretty sure that was it. Okay, let's take this out. This fancy little guard. And hopefully we should see that like the end state is still drawn. Spam, 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 spam. Yeah, we're chilling. Okay. Okay. It's actually really fucking easy. Okay, so now we want to draw the backwards pass. So once we get here, we have to walk backwards we can kind of assume that it went boom, boom, boom up here, then to the left. And it would be nice to kind of draw that whole thing. So where does that come from, I guess? Lib, diff, lib. We have like our debug info. And do we have to draw, do we have to do anything special here? We could just add more line segments in the backwards, like for the backwards pass. So we could do something like, we basically just want to do whatever we're doing in our like diff thing here. So here we do like this backwards pass thing, which looks a lot like the forwards pass, except with some like actions that we're taking where we're writing down what happened essentially. And so I guess we could maybe abstract away this backwards pass. And maybe like we could make some function that runs the backwards pass. Which I guess would live around here. And we could say like function. Ooh, I don't know, man. Diff backwards pass. I.e., how do we, maybe we'll say walk Myers trace. I like that. Walk is like a good word for what I'm trying to do here. And I guess we start at some D and K value. And we take in some function, which is going to take in, I don't know, something. So we're just going to call the function at each step. Sure. And I guess, what are we want to look at what is this guy doing? So he's saying that if he's basically doing as a function of everything is a function of previous x and previous y and the current x and y. So I guess here this is going to take in I64, 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 I64. Sounds like an iterative trait. Maybe. That does sound kind of nice, because then you get like the lazy evaluation as well. So you could frame this as an iterator that emits positions. And do I want to like emit like the movement, or I guess I could just emit like the current position, and he could. Yeah. I kind of like that. So I could make it an iterator that just emits x and y's. So you could have something like. I suspect that you could do this in like the forwards pass as well. What is the forwards pass doing? It's like kind of different. Maybe we'll find some commonalities later, but for now, we'll pretend that we're in like exploration mode, which we kind of are. Even though this algorithm is already implemented in the code. We'll pretend we're in exploration mode. So we'll call this like Myers backwards iterator. And he's going to have like a reference to the trace. Okay. And he's going to have some like D and K position. And what else is he storing here? He's storing his X and Y. Okay. So now we want to implement iterator for this guy. We don't really care about his lifetime here. And we need to implement missing members. Okay. And so each thing is going to emit like an X and Y position. Uh-huh. Yup. And D. So he's going backwards in D. Okay, so he's going to start with the maximum D value. I guess we'll impl the new function first. Which will just take in like D, X, and Y. And he's going to return a Myers backwards iterator. Okay. And Myers backwards iterator. And we just fill in values. So D is D, X is X, Y is Y, and K is whatever we calculated K to be at the beginning here. I guess K is kind of implicitly calculated at the top of the loop, so you don't have to store it. And of course we need the trace that we are getting the data from. Okay. Yup. And so let's start by like integrating this with like the diff algorithm. Because the idea is that if our like existing tests for generating diffs pass, then we like probably implemented the iterator correctly. So we're gonna say that the back diff, we'll just call it IT. And he's going to take in D, starting at the shortest edit distance, and then X and Y, and the trace. And then he's going to do something like let last is equal to IT next. And so that should give him previous X and previous Y. Maybe. And then our loop is going to look something like for X, Y in IT. We're going to do something like last 0 is equal to X. We'll do this. We'll say let mute last X equal to last 0. Last Y is equal to last.y. And I guess these were called prev-X and prev-Y before. And I guess we say let OK last. If there's no thing, I guess we can assume this exists. I think. I'm not really sure. Not positive about this. So at the end, we're going to say prev-X equal to X, prev-Y is equal to Y. And then what else are we doing in here? This walk part is going to be done, but we have to kind of like push a traversal for each of these. Okay, I see. Okay, that's fine. So this stuff is going to be handled from within the iterator. We're going to step node by node. What is this path? Is this used anywhere? This looks like just kind of like leftover code from like a previous implementation. Right, like if I just delete path here, nobody knows, okay? So I guess here, we're going to say if prev-y is equal to y, we do this. Fuck, wrong spot. If, fuck, my indexer's broken. if prev y is equal to y, we push a removal. This is probably going to be an else if. We're going to say if prev y is equal to y. No. If prev y is equal to y, we push removal. Else if prev x is equal to x, we push an insertion. Of prev y. And I guess we're going backwards, so the previous is actually the current. Yep. And then else, we push a traversal. I think. We'll see. I'm not really 100% on this. And here we should probably assert that x is greater than or equals 0. Y is greater than or equals 0. Otherwise, these casts won't work. Seems simple enough to me. Okay, so now we just have to handle like actual stepping through the iterator. So it's something like this. Oops, wrong spot. This is in here. So here we calculate x, which is from self.x and self.y. Or sorry, k. Yeah, we get the previous k from the trace. Easy. Everything here just becomes self. So here's where it gets tricky, is we had a while loop in here. And now we have to... While x is greater than previous x and y is greater than previous y. Like, what is going on here? Ah, okay, so saying if this is a diagonal, we traverse. So I guess here we kind of have to step each traversal. Okay. So it's something like, we have like a line segment. This is going from like this section of the graph to this section here. So they're kind of saying like, okay, so I have like this point and this point, and I know that while both my x and y are wrong, then I can keep going diagonally. So we can, maybe in our iterator, get the previous x, get the previous y, and we can say if self.x is greater than prev x, and self.y is greater than prev y, then we adjust our self.x and self.y, and we do the same thing. If y is less than 0, self.y equals 0 to prevent going off the edge. I don't know why we only do this for y and not x, but I won't question it for now. And maybe that's just fine, and then we just return self.x and self.y. And what's like the end case of this iteration? If we have to decrement d at the end of this, so this has to be else self.d minus equals 1. And I guess we can just say at the top, if self.d is less than 0, we return none. Now, I think it's very likely that this is wrong. Like, extremely likely that we fucked up an edge case here. So what we can do is we can, I guess maybe what makes sense is to comment out the old version of the loop here for reference. And then run the tests. Cargo test. And probably they'll fail and we have to debug. And maybe then we can debug with visualizing. So here... Oh, god damn it. That's fucked. Oi! What a pain. What a pain. I mean, I knew this was going to happen, but I hate it when it does. It's nice when it just works. I don't even know where to start. I guess we can probably we can start looking at the we can try to hook it up to the visualizer, which might give us some clue. Which we could do by maybe for a given D and K, we could maybe just start running the backwards pass. So instead of what we're doing here, we could just say let backwards iter is equal to Myers backwards iterator, new, self D, and we need to like look at the X and Y. So it's like X, Y, and self trace. And then we do the same thing. So we look at the first thing. Yeah, so we'll look at prev X, prev Y equals this. And then we generate the steps out of this. So we say, I guess the steps are kind of like encoded in this already, actually. We kind of just say let steps for K is equal to backwards iter. I guess we have to reverse it and then collect it. But we can't reverse it. But we can collect it into a vector of I64, I64, and then reverse that. Yeah, yeah. And I think that might just kind of work itself out. At the very least, we'll see something that's interesting. Let's go here, we go here, and we're seeing nothing, which is bad. So we could even look at here. And we can just start logging stuff. Okay. Let's just see what fucking happens. Next. So here we're seeing D0, X0, Y0, and then there's nowhere to draw lines from, which makes sense. Here we see D is 1, X0, Y1, and then we see D0, X0, Y1. Twice. So we never see D0, X0, Y0, which seems like a bug, right? We should be drawing from here to here. Y is never decreasing. Right. Because we're never decreasing K. Our loop here was saying for D in this, Let k is this. Let prev k is this. We're missing this case here? No. What the fuck am I missing? So k gets decremented d k. K is equal to x minus y. So we're looking at d. Why is y never going down? Y is only ever decremented in this case, and I guess kind of implicitly by this case. Hum. So this kind of makes sense. We're not hitting this because there's no traversals, like no diagonals. Prev x. I guess we kind of need to log what like prev x and prev k are and stuff. So we'll say prev, or k is this, prev k is this, prev x is this, and prev y is this. Oh, we're never assigning here. Here we need to say that that's what I think we're supposed to. X equals prev x, y equals prev y. We're not hitting this. So here we just need to say self.x is equal to prev x and self.y is equal to prev y. I'm pretty sure that's it. Pretty sure, but we'll find out pretty quick. Boom, 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 boom. Okay. We're somewhat close. That looks a lot better. Not quite right, but better. Better, better, better. Can we maybe... There's something, let's look again. Let's delete this print line because it's bothering me, and maybe we can just kind of try to intuit what it's doing wrong. So here we start here. We expect it to go here next, which it's just not doing. Then it goes... I think we're not returning the first iteration. I think we're missing... If we're at the first iteration, we have to return self x and self y before modifying it. So I think that's the problem. So for now, is there a way to like kind of encode the first iteration here? We can also just do like if first iter self first iter is equal false and return sum self x self y, which I'm not like the biggest fan of. Not the biggest fan of it all. But it does get us out of this. But I think that any time that you're doing a first iteration thing in a loop like this, you're doing something fucking wrong. Like, pretty fucking sure. Like, this feels wrong no matter what. So, fix me. Surely we can encode this information without this bool. But I do think it solves my problem. Boom, 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 boom. Hell yeah. Look at that. Wait, that's so sick. So we're seeing like the whole path we took at each node on the graph. That's so fucking sick. That's so sick. And so like now we're like technically drawing the backwards path at the end as well. That's super fucking cool. Okay, so let's try with like a different diff. So here can go like A is going to be like 1, 2, 3, 4, 5, 6, 7, 8 or something. And then we can say we're going to have like 3, 4, 6, I don't know, 6, 6, 5, 1, 2, 9 or something. I don't know. Fuck it. Like, who cares? Let's just kind of see what happens. Let's just see what kind of... Okay, so we've got our little graph, and let's first like sanitize the graph. So here we have 2, we see 3, 3, 4, 4. Those are getting diagonals. We're seeing 5 is not 6, 6. And here we see 6, 6 again. That's getting a diagonal. Great. 5, 5 gets a diagonal. 5 to 1, 1, 2, 2. Yeah, so it looks like the graph's being drawn correctly. And we can kind of just start stepping through here and see... Oh, that's so fucking cool, man. Oh my god, that's so fucking sick. Oh, baby, hell yeah. So you can kind of see that, like, the algorithm just, like, immediately ignores all of this stuff, I guess, unless it's going to come back for it later. So why is this never getting hit? There's no, like, because it found this diagonal, I guess? Hold on, let's go back to the beginning. So, k, negative 1 to 1. Alright, this is, yeah, negative 1 to 1, negative 2. So here, it should hit this node right now. Oh, so this is a branch from here to here. Okay. And then it goes here and goes whoop, all the way down here. So this node has been hit, but we kind of lose that information because it's like not relevant to any of the things we're looking at right now. So probably now we're going to see it go here. Okay, so so it skips this one because of the fact that there was this diagonal above it. So it looks like probably anything with a diagonal above maybe just doesn't get hit because of like the way the algorithm... It does kind of look like that, eh? So we're kind of never going to see... I'm just pointing at my screen with my finger like a fucking idiot. I think that we're never going to see anything in here get hit until this diagonal. Oh, we did see this one. Oh, because it's branching right from here, though. Very interesting. Very, very interesting. So I guess that's part of the, like... The like, intelligence of the algorithm. Is that it's like skipping a whole subset of possible areas of the graph. That's pretty fucking cool. I don't like how much time it's wasting going outside of the bounds, so there's definitely a fix, like an optimization to be done there for sure. Are you following a tutorial for this? Kind of. So I read through these blog posts by James Coughlin a while ago, like a year ago when I implemented this first time. And this is like a very good explanation, but in reality, this here is almost good enough to implement the whole thing. Like, because you don't really have to understand it, to be honest. Like, let's see, is there like a place where the whole thing is just written out? Like, you can almost just copy paste it and say, like, you can like black box in your head and go like, well, this is an algorithm, and I just need to understand how to use it. Which is why I'm doing this visualization, because that's kind of what I did last time. Is like I kind of like got it enough to implement, but not enough to really understand. This blog is how I learned. Excellent resource. Yeah, I don't think it's wonderful. This guy's, well, godsend. Because everything else I read on was like kind of felt too academic. He kind of put it in terms that I can understand as an idiot. Okay, so what is the next step here? The next step is probably, I think we've kind of got enough in place to start implementing the backwards pass. Sorry, not the backwards pass. Okay, so like the linear version of this, what he does is essentially he just does what we're doing here, where we go like boom, 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 boom. He does that same thing, but from the other side at the same time. And so like every time I hit the next button, what we're going to implement when we do the linear side is he's going to go from this side and we're going to see bump, 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 right? Like bump, 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 bump. And eventually they're going to like slam into each other. I think, if I understand it correctly. And so what you do here is like the expensive part of this algorithm is keeping track of this, like all of these lines that I'm drawing here, right? You need to keep a lot of state to be able to draw this backwards. But if you're just kind of iterating, you kind of only have to remember the last section and the last two diagonals at any given time, because you only ever have to look at like where was I last step? Now where do I go to this step? All I have to do is look at the last thing. And so like the if I understand the linear thing correctly, which again I might not yet because we haven't implemented yet, you run the algorithm once with only keeping track of like a little bit of information, the only information you need to iterate. You smack into each other, and then you say, okay, so this smack point, I'm going to bisect my problem now, and you can kind of like draw like export color paint. You can kind of do something like say you collided like here. Oh, I wish I could fucking, where's my pens? Oh, okay, red. We'll try red. Still black. Great. Oh, because there's two of these fucking floating ass windows. Okay, we'll try this one. So you could kind of like draw a box. Imagine, oh my god, what am I doing? Imagine that you collided here. You could draw a box like maybe like this and a box like this. And now you have like the same diff algorithm can run, but in like these two smaller areas. And you've kind of chopped out a whole bunch of like irrelevant space by doing that. And so now you're like quadratic memory usage becomes a lot more manageable. So I think that's probably where we'll go next, but I don't think that I'm going to make useful progress on there today, and I need to do some off-screen reading just to double check that my understanding of this is like good enough. So I think I'm gonna call it there. I'm pretty fucking pleased with this visualization though. That's super sweet. Like, oh, it just feels so good. So if you like what you saw, I stream most days at around 1 or 2 o'clock Pacific time for 1 or 2 hours. Right now we're working on this, and by extension, the Git GUI that we're working on. Eventually, we're going to have to get back onto our terminal emulator, but I have a couple more things that I want to do on the Git GUI first. There is a YouTube link in the Twitch description where we have playlists of all of our previous projects. So we've kind of done a lot of things on this channel. We've looked at operating systems, we've looked at neural networks, we've looked at virtual file systems, like, oh, I'm already forgetting, 3D geometry of some form. Yeah, there's whatever I'm interested in, right? So I've got, I think that there are like infinite problems to be solved, and so it's kind of we cover them piece by piece. So yeah, you check out the YouTube. There's a GitHub link in the Twitch description as well, where there's like code that's associated with all these projects. And if you're watching on YouTube, there should be a Twitch link in the YouTube description where you can swing by and say hi if you happen to be online between 1 and 4 o'clock Pacific time and feel like swinging by. I think that's it. We'll be back tomorrow to try to implement linear diff. Otherwise, thanks for watching, and I'll catch you on the next one. Bye!